In previous parts, I explained what is 0-1 knapsack problem and how we can solve it with backtracking algorithm. I explained it with several examples. Now, today I will give the main backtracking algorithm to solve 0-1 knapsack problem. Okay, so here just I am writing K knapsack and it will take three parameter. One is K and the current weight and current profit. Okay, current weight and current profit. Here first see, you can compare. This is the example what I discussed in the previous part or in part 3. What is the state space tree for this state space tree for this example. So for writing this algorithm, take the help of this state space tree. So initially this knapsack function will be called from the main that 1 0 0. The value of k is 1 and the current weight is 0 and the current profit is 0. Okay. So first it will check for the left branch whether the left branch is feasible or not by checking if CW plus WK CW plus WK is less than or equal to M. What I did, see here. Now at this time the control is here, CW is 0 and the W1 is here 2. So 2 plus 0 2 is less than 12. So this condition is true. When this condition is true, then it means the Y1 is 1. So here I will set YK. K is here first time 1. Y1 equal to 1. Now as I said that if K equal to N, it means there is no recursive call. You are at the leaf node. You get one solution. So before calling the recursion, we check whether K is less than N or K equal to N. Okay. So this left branch can only be called if K is less than N. Okay. So here the condition to be checked, if K is less than N. If K is less than N, then simply the same function will be called for the left branch. This is for generating the left children. Here this condition is required for generating the left children. If K is less than N, then K nap and K plus 1 CW plus WK and CP plus PK. If this condition is true, then the function is called K nap K plus 1 CW plus WK. This is the next updated weight and CP plus PK. Okay. If K equal to N, K equal to N means you are here. You are here. Here when the function is called for K equal to N. Here the value of N is 5. It means you are at the leaf node. So before generating the leaf node, you have to check the profit, the current profit, what is generated, what is stored in CP should be greater than the profit of the solution vector generated so far. So here if K equal to N and K equal to N and CP plus, here we are taking the decision for fifth, the CP plus PK is greater than, CP plus PK is greater than F. Then only just what we do, if CP plus PK is greater than F and K equal to N, it means this leaf node is giving the better solution than the previous leaf node, as the solution generated, the profit of the solution vector generated so far is stored in F. So we generate the leaf node, and this Y will be overwritten to X only if the profit generated by this leaf node is greater than F. Then we take one variable F final weight FW equal to CW plus WK, and also F is updated, F equal to CP plus PK. Okay, and then for the this yi's to be overwritten to the x, as I get the next, I will get the next solution vector whose profit is greater than the previous solution vector. So this yi's to be copied to the xi's, or we update the previous solution vector by putting all yi's into xi's. So here for I equal to 1 to n y xi equal to yi. Okay, see this is for, this code is for left branch. Okay, now for the right branch, when you are going to the right branch, now here is the question whether to move to the right branch or not. So simply the some upper bound is used. So that bound function here at this point for the right, this bound function, what I explained in the part 3, that this bound function is called for what? For that the kth weight, here the kth weight is removed, and 1 to k minus 1, or for object 1 to k minus 1 already decision have been taken, and kth weight is removed, and the from k plus 1 to n we compute the profit by relaxing the condition from 0 1 to fraction. Okay, so here the bound for the right branch, this is for left branch, this code is for generating the left children. Here for the right children, if, don't use here else, because for every object it will check for the left as well as for the right. So if, and the bound function will be called bound k, that is CP CW is greater than F. Okay, clearly note down. Here I explained in the part 2 that we move only to the right direction if the bound function is returning the profit, and that profit is greater than the profit of the solution vector previously generated. Okay, so if this solution vector is, if this profit is greater than F, it means there may be the chances to get the better solution. It is not always the case, because here I have relaxed the condition and solve the problem by taking the fraction of the object which is not fitted. Okay, so here this is the right branch. Right branch means the kth object is not included, that is yk equal to 0, it is excluded. Yk is equal to 0 is means the kth object is excluded, and again if k is less than n, if k is less than n, this function again called k knapsack, k plus 1 because there the object is removed, so simply here the same CW and CP is passed because the kth object is excluded. If k equal to n, okay, here you can put the k is less than n, here we can put else. It is not required if k equal to n. If k equal to n and Cp is greater than f. See, here I have used only Cp because the kth weight is excluded. Okay. If k equal to n, then the same code is copied. Fw equal to Cw and F equal to Cp for I equal to 1 to n. It means k equal to n and Cp is greater than f. It means for the right branch I got the solution better than the previous one. So we update the final weight, final profit, and the solution temporary solution vector is copied 1 to n xi equal to yi. Okay. Here this set and this final end. Okay. See, here this is visible. I equal to 1. See, if k equal to n and Cp is greater than f, then Fw will be Cw. F is the final weight, f is the final profit of the solution vector generated now, and the yi to be copied to xi. This is for right branch. So this code is for the right branch. This is if, and this is this if, and this simply here. Okay. Now you can drive with this example, this algorithm. See, first time the algorithm will be called as what? 1 0 0. Okay. Cw plus wk, that is Cw, here k is what? This time k is 1. Okay. So Cw is 0, 0 plus 2, 2. Okay. So yk equal to 1. So y1 equal to 1. If k is less than n, yes, k is less than n. So simply k plus 1. Now the left recursive call to be called with updated value of weight and profit 2 to 14. So the next time the same function will be called with 2 to 14. Now again this will be checked. Cw plus wk. Cw plus wk is 2 plus next is 3, 8. That is less than or equal to n. So y2 equal to 1, k less than n. So here simply the k plus 1, the same function is called with next object k plus 1, Cw, that is 2 plus 3, 5, and the profit is updated profit Cp plus pk, 14 plus 18, that is 32. Okay. Now just now again the function will be called at this point. So here Cw is 5 and the next weight, third weight is 8. So here 8 plus 5, 13. So this condition is not true. Carefully see, this condition is false. So here for this case, when k is 3, we cannot move to the left branch. So here directly, here I have not written the else. So for this case, the right branch to be checked. Now for the right branch, first the bound function is called. Here in the bound function, now see carefully, before calling the bound function, the 1 to k minus 1, here the bound function is called for k equal to 3. So it means this 1 to 2 objects, the decision have already been taken. Some of the yi's are 0, some of the yi's 1. Now the bound function is called for the right branch, so the kth object is removed. Here x1 to xk minus 1, for object from 1 to k minus 1, the decision have already been taken and the kth object is removed. Okay, and this function return the profit if we relax the condition for k plus 1 to n object from 0 to 1 to fractions are also allowed. So as simply see in the bound function, if the weights can be fitted into the knapsack, then simply we put the whole object into the knapsack, and the next object which cannot fit, we take its fraction and compute the profit. Okay, here some students are having doubt that why just we are relaxing the condition. So one thing I told in the part 1 that when we solve the problem using a greedy approach by relaxing the condition from 0, 1 to fraction, so we always get the maximum profit. It means when the fractions are allowed, then the knapsack will always be full. But if the fractions are not allowed, then the knapsack may or may not be full for the optimal solution. So we always get maximum profit when fractions are allowed. Okay, so now here just our objective is to decide whether to move in the downward direction or not. Okay, so far whatever solution I am having, say here that at this time there is no solution, so simply y3 equal to 0 at present. For this case you can check bound function, whatever bound, because initially f is -1, at present no solution vector is generated, so f is -1. Okay, so whatever with the bounding function it will return the CP. Of course this is greater than f. So here this y3 equal to 0 and k is less than n. So k nap, again this function will be called with this 4, 5, 32. Now y4, again CW, that is 5, and fourth weight is 4. So 5, 5, 4 is less than or equal to, so y4 equal to 1, k less than n. Again this is called with updated value of CW and CP. Again now here the CW, that is 9 plus 2, 11. So this is what? Less than or equal to m. Yk equal to 1. Y5 equal to 1. But this condition is false. Here k equal to n. K equal to n. So this will be checked. Again Cp plus Pk. At present Cp is 44. 44 and the profit of the object 5 is 3. That is 47. So 47 is greater than -1. So here one solution vector is generated whose final weight is Cw plus Wk, that is 11, and the final profit Cp plus Pk, that is 47. So here f is updated as 47, and the same because I get one solution vector, so yi is to be copied to the xi. So one solution vector is what? X, that is 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, and its profit is 47. Okay, so now here after this simply just here if k equal to n, then it will reach there. Okay, and simply the condition is true. So for this case again the right branch to be checked because there is no else. After returning this, for the same k equal to 5, right branch to be checked. For the right branch, the bound function is called, and the bound function will return, you can check it, 44, and 44 is less than 47. So here this right branch will not be called. Okay, so this condition is false. So here this code will not be executed. Okay, after that the stack to be checked and the previous k value will be popped. So here the previous k value is what? The 4. For fourth, the left recursive call is okay. Now for k equal to 4, this condition is delayed due to recursion. So this condition will be checked whether we can move in this direction or not. Now carefully check here. Bound function will run from 4 and 5. At present the profit is 32. Now we can check that if we apply the bound function, then the k plus 1, that is fourth weight is excluded, and simply we are having at the fifth. So simply 32 and the weight profit of the fifth is 3. So simply 32 plus 3, 35. So this is less than what? 47. Bound function will return here what? 35. And this is what? This is less than f. So here this right branch code will not be executed. Now again the function is terminated and the stack to be checked. So here the value of k is 2. For 2 the right branch is with the feasibility of the right branch to be checked from the bound function. So here the bound function will be called, and when we call the bound function will be called for what? 3 to 5. 3 to 5. So here 3 to 5 we get the profit as 49. So it means we can move to the right branch. In this way you can try. Now just again, if you are having a doubt on the bound function, simply just what actually the criteria, if you are at here at any particular point and you are considering right branch, okay, if you are considering right branch, then our objective to apply some upper bound on the profit, so that we sure that on going downwards we get the solution better than the solution vector generated previously, because this is the optimization problem and only one leaf node will give you the optimal solution. So how we can get the upper bound? So what I did, because if from k plus 1 to n, here in the bounding function you check what I am doing actually, from k plus 1 to n, just we are adding the objects as the weight and current weight. Current weight, this k plus 1 to weight, and the weight of the objects from 1 to k minus 1, whatever this is Cp, that is Cw is less than or equal to m, then we add it. If it is not fitted, then we take its fraction and we compute the profit. See, and now whatever is the profit, that profit is generated by relaxing the condition from 0, 1 to fractions. So we are getting whatever with the profit, that profit, if suppose that profit is less than the profit of the solution vector which is already generated, then we cannot get the better solution and we will not move in the right branch. Okay. Now here when you execute this algorithm, carefully see here in the knapsack problem, just whatever be the main, in the main function, if you write the main function, then simply here in the main function you declared all variables global. Always remember that y should also be declared globally. Okay. So here when you write main, okay, so before main int w weight vector, profit vector, and weight vector, profit vector, and number of objects, knapsack capacity, final weight, final profit, and weight, profit, n, m, final weight, final profit, and y vector, the temporary vector, all should be declared globally. Okay. Here in the main, simply first you ask from the user what number of objects, printf number of objects. Okay, number of objects, you take the number of objects. The second is number of weights, printf enter the weight vector. Okay, weight vector here is for I equal to 1, I less than or equal to n, I plus plus, scanf. Here I have declared all as wi, and then profit vector, take the profit vector from the user. Again there are n elements, I plus plus, scanf, m%, %d, m% pi, and then knapsack capacity, printf capacity, take the capacity from the user, that is scanf %d, m%, m. Okay, so these are the input: number of objects, weight vector, profit vector, and the knapsack capacity. Finally, you initialize the final profit as no solution vector is generated. So this variable is declared globally, and before calling this function, you initialize f equal to -1 and simply call this function k knapsack with parameter, actual parameter 1 as you take the object, and 0, 0. Okay, we call this function with 1, 0, 0, and because this is a optimization problem, so no solution is printed, but finally it will return the one optimal solution vector in x. So after that, here you declare, here you write for I equal to 1, I less than or equal to n, I plus plus, the optimal solution is printf %d xi. Okay, get ch to hold the screen, and simply this one. Okay, now here one more thing, you give the weight vector and profit vector according to the decreasing order of profit per unit weight. Always remember that in the backtracking condition, it is required that you have to arrange weight and profit vector according to the decreasing order of profit per unit weight. So at the time of giving input, remember that if suppose in your problem profit and weight vectors are not arranged according to the decreasing order of profit per unit weight, so first on the copy or paper you arrange the profit vector and weight vector according to decreasing order of profit per unit weight, then you give the input. Next here, this is the main function. In the knapsack function, you call what? Bound function. So here the prototype of the bound function you declare globally, like bound, and before here the simply your header file declaration int. Okay, and from this function, from this line, you declare the local variables like I. Only there is one local variable int I, and just you give the knapsack prototype here, k knapsack int. Okay, and declare I. Okay, so here this is the prototype declaration of the knapsack function, because within the main knapsack, because bound function is called and this is a recursive function, so I avoid to declare here the declaration of bound function, so I declare the bound function globally. So you write main, the second is the knapsack function, and third is the bound function. In the bound function you take B and C as local variable, K is the objects, and K is the object, and CP is the current profit, CW is the current weight. Okay, so now you can dry run this algorithm on all previous examples I have discussed so far. Okay, and I want that just you execute this algorithm by trace or dry run this algorithm by maintaining the stack and drawing the state space tree, and I will give the problem what you can solve using backtracking algorithm. Okay, thank you.